Great. I want to thank the organizers for inviting me to come down here. This is my first time here at Santa Barbara. And I think in Eric's email to me to invite me, he asked me to explain planetary chemistry for everyone else. So it's a big topic. And I'm going to expose my bias here. I mostly work on the small rocky planets, so that is the kind of chemistry I'm going to focus on here. And I had to narrow it down even much further than that, so we're going to focus specifically on the geochemistry of the volatile elements as they would behave on a rocky planet. So to sort of get us all oriented, and since this is my first time here, I hope I've pitched this correctly. We're gonna do sort of a crash course in how a planetary scientist thinks about chemistry of the elements. But first, we'll start with the astronomical classification of the elements, since I imagine most of you think of yourselves as astronomers. And of course, we have hydrogen and helium, and everything else is a metal. Okay, we're done. All done. But this is not how people who work on the planet underneath your feet think about this, of course. So the question is, what are the planets actually made out of, right? This makes sense when you're studying the universe at large, and most of what you can see are the hydrogen and helium. But so here's two planets we have in our solar system. What are these planets made out of, right? So we've got Jupiter on the right. By mass, Jupiter is mostly hydrogen and helium, so you guys got that right. And everything else is a few percent at best. But the Earth, our small little orb over here, what is the Earth made out of? Well, it's mostly by mass, it's iron, right? Second most abundant is oxygen, and those two each make up about 1/3 of the mass of the Earth on their own. And then magnesium and silicon combined make up another 1/3 or so. And everything else, there's about 7% of everything else would be considered minor or trace elements, right? And these two elements, iron and oxygen, those are going to be the most abundant elements in every rocky planet that looks anything like the Earth, right? There are certainly possibilities where that might not be the case, but those two elements are always going to dominate a rocky planet. They might switch order. That's a possibility depending on the amount of metal they have in their core. That's where most of our iron is. If we had a bigger iron core mass fraction like Mercury does, iron would be a larger proportion compared to oxygen. If we had a smaller core, then oxygen might be a little bit more abundant than iron. But it's always going to be those two elements. And so let's look a little bit deeper into the chemistry of these planets. I'm going to go through two more periodic tables. So this one is how cosmochemists, the people that are looking at the condensation of dust in your protoplanetary disks, think about the classification of the elements. And they do this by thinking about the temperature at which different solid materials form in the disk. And so the colors here are defining temperature ranges at which these elements are condensing. This is based on calculations of the 50% condensation temperatures of these elements in a solar composition gas. If you change the gas composition, the ordering of these might actually change. Purple are very highly refractory, and blue are also refractory. These condense at very high temperatures. And greens are moderately refractory. And so you get things like calcium, and aluminum start to condense at really high temperatures, and this is why you get calcium aluminum rich inclusions as some of the most high temperature condensates from the solar nebula. Other things like magnesium, which is a major component of the Earth, are a little bit less refractory. They condense around 1300 to 1500. And other things would then become volatile, moderately volatile to just volatile to highly volatile as you go to lower and lower temperatures. So hydrogen and helium here are highly volatile, right? They don't condense until much, much lower temperatures than the stuff that makes the solids. Now, a geochemist actually has a different picture of this and a different set of classification terms. And this was established sort of in the 1930s by really the father of modern geochemistry, Goldschmidt. There's a whole conference named after him in geochemistry, Goldschmidt. And the geochemists classify elements based on the phases that those elements want to go into in a particular chemical environment. And this is definitely sort of biased towards Earth-based chemistry. So the terms you've probably run across before are lithophile, siderophile, and chalcophile. And these are talking about the phases that the elements that make up most of the solids want to go into. Lithophile means rock-loving, and so we have all of our rock-loving elements in green here. So calcium, magnesium, aluminum, silicon, those all want to go into rocks. Metal-loving is siderophile, that's the reds. So iron is basically the metal that we think of when we think of our core. And we have a lot of cobalt and nickel also in our core. And then the purples are chalcophiles. These want to go into sulfide phases. And for the Earth, most of those sulfides ended up in the core as well. And so those are sulfur, selenium, tellurium, but things like copper, silver, etc. And then the volatile elements are in the yellowed. And here they're called atmophiles. These elements want to be in the atmosphere. So on the Earth, hydrogen and all of the noble gases really kind of want to be in the atmosphere. And we have carbon and nitrogen as well. So you can see that all of these elements have, or most of these elements also have a small extra little box in the left-hand corner. And these are sort of their secondary tendencies, or tendencies they might have in other chemical environments. So carbon is also listed as an organophile. But it's also got a little red square, right? It could also be siderophile. It could go into metal alloys. So the elements I'm going to focus on today are hydrogen, carbon, and nitrogen as the ones that make up the bulk of the atmospheres of the rocky planets. And we'll talk a bit about some of their chemical tendencies within a rocky planet sort of environment. So to do that, let's talk a little bit about, just briefly, about the chemistry of rocks. So rocks are silicates in general. They're silicate minerals. And the basis of all silicate minerals is a silica tetrahedra. It's a little silicon atom with 4 oxygen atoms around it. And this unit has a negative charge of 4-. So a silicate mineral has a bunch of these little pyramids that are stacked in different configurations to give us different mineral structures. And they're all bonded with different cations, or elements that have a positive charge. And the elements have positive charges depending on which column in the periodic table they are located in. So the ones on the far left-hand side are alkalis. They take a +1 charge. The alkaline earths, calcium and magnesium, take +2. And so calcium and magnesium want to bond with 1 oxygen atom, which has a 2- charge. And so if we want to bond it with an SiO4 unit that has a -4, we need 2 of those magnesiums, right? You'll notice iron is on here twice. Iron is the most abundant element in the Earth that can take 2 different charges in typical silicate minerals. There are other elements can do this too, but iron is the most abundant. And this is an important part of the chemistry of the Earth's mantle. And for the Earth, the major element geochemistry is really defined by 8 elements. It's oxygen plus all of the cations, the magnesium, silicon, iron, calcium, aluminum, titanium, and sodium. And everything else is considered either a minor or a trace element. They're minor or trace if they have abundances sort of below about 0.5 weight% in a particular rock, okay? So these are the major elements that determine the chemistry of a rocky planet. And the structure of a rocky planet on the inside is separated into these different phases. So in the center, of course, we have the metallic core, we have a silicate mantle, we have a crust that is also silicate minerals of lower density, and then for the Earth, we're fortunate we also have the ocean and an atmosphere on top. And you don't have to remember any of these mineral formulas, but I figured I would put them up here just for everybody to at least get a little bit of familiarity with what are the major actual minerals present within some of these layers in the major element chemistry. So the mantle is dominated by magnesium, iron, silicon, and oxygen, mostly in this mineral olivine, which goes through at high pressures. It transforms into slightly different mineral structures that give it a different name, so wosleyite and ringwoodite, as you go deeper into the mantle. We also have pyroxene, which transforms into bridgmanite at high pressures, and a variety of other less abundant minerals. If we go to the core is the major element chemistry of the core is that it is an iron-nickel alloy. Right? Nickel is a major element in the core, although it's not a major element in the mantle because it has an abundance of several percent in the core. Of course, we have our ocean, which is mostly water, has lots of trace elements within it that we'll talk about a little bit. And then our atmosphere has a lovely mixture of many different gases, but it is a single phase, right? A single gas phase. And so most of our volatiles are concentrated really in these upper two layers, the ocean and the atmosphere. But they can actually be incorporated within any of these layers as a trace element. And we're going to talk a little bit about trace element geochemistry on the next slide. So trace element geochemistry, the major elements determine the phases that exist, and then the trace elements just sort of join in where they can. So trace elements are followers, not influencers. So the major elements make the rules, and the trace elements just tag along. And so to sort of zeroth order, we can actually treat all of trace element geochemistry with Henry's law of ideal solutions. And Henry's law is a very simple equation. It just says that in any given solution, the pressure of a gas of a particular component is directly and linearly proportional to its concentration in that solution. So the green line here is a real solution where we're looking at the concentration of a component going from 0 up to 1. And Henry's law is given by this line here. So Henry's law really applies at low concentrations, which is why it's appropriate for trace elements. And this constant, the Henry's law constant, it has to be determined empirically for every component of every solution individually, which is why it's complicated, right? So we can treat water as a trace element in the Earth's mantle. And so we do know that there is relatively abundant water in Earth's mantle, maybe as much as 2 to 3 times as much as there is on the surface. But it's not evenly distributed throughout the interior. This is a graph showing the potential storage capacity, although not necessarily the actual content, of Earth's mantle in terms of water content. You can see that there are regions where we could potentially store a lot of water, like this small region between 400 and 600 kilometers depth. You could also put an awful lot of hydrogen into our core based on experiments. And so, where are we going with this? And this water is distributed in different ways within the mineral structures of the major elements in the Earth's mantle. And when we say water here, most Earth scientists just mean hydrogen in some form. It could be an OH group, it could be an individual hydrogen atom, it could be an actual hydrogen or water molecule. But it's stuck in sort of different spaces in the mineral lattices for solid minerals in different ways. So it could bond to one of those oxygens in those silica tetrahedra. It could go into the spaces in between the cations, depending on the mineral that we're looking at. So water and other volatiles can dissolve into solid minerals. They can also dissolve into silicate melts. So We know that this is also true for water, for CO2, for nitrogen, for sulfur. And like with the minerals, we can treat this mostly as a Henry's law type situation, but empirical measurements have shown that it deviates from that considerably, especially for water here, which goes well beyond the trace element abundance level. You can see that this is a fraction or a mole fraction or mass fraction going from 0 up to 50% for water in basaltic melts. So you can stuff a lot of water into silicate melts. And we can see that the actual solubility that's been measured deviates pretty strongly from the Henry's law once you get above about 10%. Okay, CO2, in contrast, is much less soluble in silicate melts. And Henry's law is only good for it up to about 1%. Okay, so to zeroth order, we can treat it as Henry's law, but it definitely strongly deviates from that. So in general, we need empirical relationships for these solubility laws in order to treat this. Now, why do we care about all this in terms of thinking about planet formation? This is a great graphic that Tim Lichtenberg created for our recent Protostars and Planets chapter that was on the geophysical processes of planet formation. And so this looks at the growth of the planet itself during planet formation. You guys mostly are working at the much larger scale. How does this stuff get there and assemble? And what we're looking at really is what is happening on the object itself. So starting from sort of planetesimal stage, growing through a giant impact stage, and through a magma ocean stage, and then into sort of the later stable habitable life of a potential rocky planet, we can see that there is a lot of processes going on, including melting, core formation, the separation of the metal towards the center of the planet based on its density. We have nebular ingassing and a magma ocean. So melts, silicate melts, are a prominent part of the early evolution of rocky planets. And volatiles can readily dissolve into both the silicate melt as well as the core forming liquid. So volatile elements then are acting as trace elements within two of the three major reservoirs within our planet, the silicate layer and the metal layer. And of course, they are the dominant or the major elements within the atmosphere. And the timing of delivery and loss of these volatiles can determine which of these reservoirs they end up in. And exactly how much hydrogen do we stick into the core depends on the timing of when the core itself is forming and when the planet is acquiring hydrogen. So looking a little bit more at the compositional evolution of the planetesimals, they go through different stages depending on when they get hot and how hot exactly do they get. This is a set of diagrams looking at sort of progressive heating of small planetesimals and the different processes that are going on within them. So if you start with a rocky planetesimal and you start gradually heating up, you will start driving solid state convection inside of it. Eventually you will get partial melting, and eventually if that heating continues, you will melt the full planet and get a magma ocean. If you have metal distributed within your planet, that metal will melt first, actually, and make your core before the magma ocean gets generated within these planetesimals. If you just have a planetesimal that has a lot of volatiles distributed within it, you can drive a considerable amount of escape of volatiles from that planetesimal. And Tim has work that has shown that you can really dehydrate a lot of early planetesimals. And when they assemble into your final planet, you'll end up with very dry planets as a result. So, this slide is, okay. And there are various modes of core formation as we go from small planetesimals up to larger planets. depending on how those planets are forming. If pebble accretion is the dominant mode of formation, we may just have a protoplanet that has previously differentiated that ends up with a small layer of melt at the surface with which those pebbles start to equilibrate, and so their chemistry will be dictated by that upper layer. When we have very large impacts, like the moon forming impact, we can melt the whole planet, and the cores of the two objects can mostly merge directly without necessarily equilibrating with each other first. And so thinking about how the volatiles are participating in these processes of core formation and magma ocean, here I've got a little cartoon where I've got a core, a solid mantle with a melt layer on top and an atmosphere, and I've got some volatiles that are being exchanged between all of these different parts. And the way we determine this in a modeling capacity is through these sort of pseudo-Henry's laws partitioning models. So at the atmosphere-magma-ocean interface, we could predict the atmospheric pressure and composition based on the solubilities from Henry's law. At the magma-ocean solid mantle interface, there is additional partitioning that happens between those melts and the minerals. And each of these are unique to every single mineral forming down there. And then we also have partitioning between the silicate and the metal as well. So some of our volatiles that are dissolved in our magma ocean are likely to end up in the core. And so again, as I mentioned, the timing of this process matters. So in a recent paper by Damanvir-Gruel, he was looking at whether you can constrain the timing of core formation and accretion by looking at the nitrogen abundance of a planet. So he was looking at two different models of accretion, one in which we have the rate of differentiation is faster than the rate of accretion. So we assume that every object fully differentiates before it collides with another object. And what happens is that nitrogen in general can partition into the core, but also outgasses a little bit into the atmosphere. And for every step in here, the atmosphere gets lost. So this object ends up nitrogen poor. If you have a different model where your object or the rate of accretion is actually faster than the rate of differentiation, then you're not outgassing your magma ocean fully in between every step. And so your final object may be more nitrogen rich because you're not losing that atmosphere every single time. And so he has shown this in this plot over here. We've got a percentage of nitrogen in the magma ocean versus in the core for the collisional accretion models and the instantaneous accretion models. And you can see always the objects that are accreting faster retain more of their volatiles than objects that are accreting more slowly. Here's the one slide where I'm going to bring up fugacity. This came up earlier. So the previous slide also had this, but oxygen fugacity, I don't have a slide explaining what it is. It's just a parameter that tells us really about how much oxygen there is sort of available to bond with other things in our planet. Is there enough there to oxidize our volatiles or not? Or is hydrogen more abundant? So in a system with low oxygen fugacity, there's low oxygen, and hydrogen might be more abundant. It will end up with volatiles that are bonded with hydrogen. So we end up with things like methane and ammonia. As you increase the amount of oxygen available, you'll produce more oxidized volatiles, like water and carbon monoxide. And if you get up to Earth-like oxygen fugacities, you'll produce water and CO2, and nitrogen with much less ammonia and methane around in these conditions. Now this is important, the oxygen fugacity is important because the solubilities of all the volatiles depend on the oxygen fugacity. So nitrogen and carbon in particular are much more soluble in our planet in the silicate melts at low oxygen fugacities than they are at high oxygen fugacities. We can also predict the composition of the atmosphere if we know the oxygen fugacity of the system. This plot is just showing the evolution of the gas composition. This is mole fractions or mixing ratio in the atmosphere as you go from something like the Earth down to something like Mercury, okay? Where you would have either water or hydrogen-dominated atmospheres. As your magma ocean outgasses, because the volatiles have different solubilities, the composition of the gas has to evolve as outgassing happens. This is a plot from Paulo Solsi from 2020, where we started off with a magma ocean atmosphere here, and as it progressively outgasses, the initial atmosphere is very carbon-rich, thank you, and becomes much more hydrogen-rich as outgassing happens. That's shown also schematically here in this other slide, showing a single magma ocean model evolving over time. So what we see is the atmospheric pressures in the solid lines evolving over time for a single magma ocean episode. You can see that water starts off much lower than CO2, and water becomes progressively more abundant as you outgas. So outgassing will drive the changes in the composition of your atmosphere. Of course, the composition of your atmosphere determines the cooling properties of your system, and so it's something that needs to be incorporated if you're looking at the thermal evolution of the planet itself. This is just a plug for some experimental work that Miriam Telis and Maggie Thompson did as part of Maggie's PhD thesis at UC Santa Cruz, where they were actually trying to experimentally measure outgassing from different planetary analog materials, in this case, a carbonaceous chondrite. So this was a model of outgassing that we had produced a number of years ago, and Maggie and Miriam actually did experimental measurements and showed pretty good agreement with the models. So another point I want to make here is that atmospheres are complicated beasts. Okay, and pure hydrogen is a perfectly reducing gas, which means it will react with anything containing oxygen and steal that oxygen away from it to some degree. There's a lot of models, and I have done this as well, where you start off with a pure hydrogen atmosphere. Of course, the solar nebula gas is not pure hydrogen, but anytime you have that happen, hydrogen will strip oxygen and make some amount of water. So Dan Shim and Tae-Hyun Kim showed that it will even strip oxygen from magnesium to make this magnesium iron hydride if you just put pure hydrogen with an oxide. So pure hydrogen is perfectly reducing, and one of the existing models for solar system planets and sub-Neptunes is that if you start with a thick hydrogen atmosphere and some amount of iron oxide in your magma ocean, you are going to create water, which may be dissolved in your magma ocean, and part of that may outgas. And you will make additional metal, which may sink into the core or may remain well mixed. This leads to large amounts of volatiles in your core. This is a model actually for sub-Neptunes, where we were trying to predict the amount of hydrogen or water vapor your planet would have in the magma, which is in the darker colors, versus in the atmosphere. And it turns out most of those volatiles are actually in the magma, not in the atmosphere. Carolyn Dorn and collaborators have since shown that this makes a big difference on the predicted mass and radius of planets. If you include this effect of dissolving volatiles into your interior, including into the melt and into the core, these are 3 different models with 3 different abundances of water dissolved within a planet. And the blue line is always where you're considering water dissolved in the surface, mantle, and core. So this makes a pretty big difference in your overall mass radius. The last thing I'll just quickly touch on is that volatile delivery and loss is always happening throughout planet formation. And we have heard about photoevaporation and core-powered mass loss, but impacts from planetesimals and giant impacts also cause atmospheric erosion. I'm just going to fly through this. You can deliver some amount of volatiles with small impactors, but they also erode volatiles from the atmosphere over time. A work by a Japanese group, Sakuraba, in 2021, showed that you could match the depletion of nitrogen in Earth's system by looking at this effect and where the volatiles are when this is happening. So water will condense onto the surface into an ocean and is less susceptible to escape. CO2 will dissolve into the ocean, will make rocks. Nitrogen, if you outgas it into the atmosphere, will be in the atmosphere and will be the most prone to escape. And so progressive impacts, this is starting from a carbonaceous chondrite with progressive impacts, will eventually drive you down to the Earth's nitrogen abundance. So let me just skip down then to my final conclusion slide, since Eric is standing up, and go back to this summary slide. So our volatile elements are acting as trace elements, but they can be incorporated into all of the reservoirs within our planet, and it's the timing of delivery and loss that determine where they end up and how much of them a planet keeps. So thank you.
Okay, thank you, Laura. And again, while people are going to the microphones, don't forget to introduce yourself. Jack?
Jack,
the first question?
Ames. In your fugacity slide, the one
Yeah,
where
yeah.
you actually focused on fugacity,
Yeah.
you have on the left part Earth 3 times at different masses in different states. And can you explain why Earth is in the 3 spots it is, et cetera? The up to 0.4
okay.
Earth masses between.
Yeah, so one of the things that core formation models on the Earth have looked at is the evolution of the oxygen fugacity of Earth's interior on the basis of trace element mobility. So here I'm talking not just about the volatiles, but also about the trace metals like nickel, cobalt, tungsten, and other things, where the composition of Earth's mantle, broadly speaking, in trace elements, is much better matched if the Earth starts accreting from reduced materials and the materials that it accretes become progressively more oxidized. So Earth became more oxidized as it grew.
Artem Agishin from UC Santa Cruz. So I have a question about the volatile elements in the iron core. I think it's not yet established if it's like hydrogen or nickel or anything else. And so models are great, simulations are better, but I'm thinking of an experimental way of finding something. And I have a friend who is a particle physicist. She told me they could build neutrino detectors that can distinguish between hydrogen and everything else. I'm curious about what you know, what you think.
Yeah, so the way people go about it right now, is a combination of experiments, seismic observations of the core right now, and some simulations as well. So the core formation models for the Earth are pretty sophisticated because we can try to match all of the different trace elements because we are here and we can sample them and we can measure things like germanium. And so generally speaking, people are trying to match all of the trace elements at the same time, which gives you a pretty strong constraint, right? There's a lot of elements out there to use as constraints. The compositional parameters that we then have to match is the density and the seismic wave speeds within the core. There may also be some feedback from magnetic field dynamo modeling. I'm less confident about that. But seismic wave speeds are, not going to be super sensitive to very trace elements. But there is a difference between, say, iron silicon alloy versus iron carbide alloy, right? So at the moment, I think those are the best sorts of observations we have to actually match data to. I'm not sure if that actually answered your question or not, but.
Bennett Skinner, McMaster University. Kind of continuing on the fugacity question, we have Earth's fugacity here from 0.4 to 0.8 Earth masses, but then all of the other bodies that are listed with a similar environment there are all quite a bit less than 0.4 Earth masses. So could you explain that discrepancy?
Yeah, so it is, oxygen fugacity is not necessarily tied to the mass of the body. It is also tied to the bulk composition. So mercury is way down there below iron phosphite -3 because it has a very high iron mass fraction, and very low just oxygen abundance. Mars, the Moon, and Vesta are all sort of in that intermediate range, again, mostly based on the bulk composition. But it is true that most of these are quite a bit smaller than the Earth. More it has to do, I think, with the amount of water that they accreted during their formation. Water is the primary source of oxygen to most of our planets, actually.
Thank you.
Other than the rocks that they're made out of, which contain most of the oxygen. Yeah. Oh, sure. Sure.
So Ted Bergen, University of Michigan. The early evolution of the Earth with the H2 dominated atmosphere, was that a determinative factor for the resulting mantle composition, or was it perhaps overwhelmed by the supply terms? Obviously a tough question.
Yeah, definitely a very, very tough question, right? It's something that a lot of people, the source of Earth's water is a long-standing issue. So one of the models for the source of Earth's water is essentially something along these lines, right? Is that we had iron oxide in the mantle, you put a hydrogen atmosphere on top of it, and you make water. So that model has been around for a long time for the Earth as well as other planets. The D to H ratio of Earth's water is obviously not the same as the sun. It's much more deuterium enriched than that. It is much closer to carbonaceous chondrites. And so there's a lot of models that try to match not just the isotopic ratio of water, but also the other volatile elements. And the abundances of some other trace elements as well, like the noble gases. The noble gases, at least some of them, were almost entirely derived from in-gassed solar atmosphere. But some of them were mostly from comets, depending on which of those sources had higher abundance of those noble gases. And I'm not a noble gas expert, so I won't. I specifically didn't say which ones were which. But we know that most of the solid materials that can deliver water will also deliver carbon and nitrogen and all of these other things, right? So there has to be a balance of, you have to get the right mix of things to match the whole system, also accounting for the other processes that might fractionate those things, right? We don't know to what degree you can actually get, we're still learning about the isotopic fractionation that happens for volatile elements during core formation, right? Is there some fractionation during that process that enriched the silicate Earth in some of those isotopes? Atmospheric fractionation obviously is a huge issue for volatile elements. You're always losing the lighter isotope. So I think it's a really hard problem. And there's a lot of people, I think, in this room that have worked on it before as well. So I'm hoping to learn more about it here.
Hi, Angeli Piet from the University of Birmingham. Thanks for the really nice talk. You were mentioning like experimentally derived solubility laws, and I was wondering what are the current uncertainties on those solubilities? Like, how do they affect our models for exoplanets? And like, what areas of parameter space do you think that like the next generation of experiments needs to go in?
Yeah, so solubility laws for volatiles and silicate melts are driven almost entirely by volcanologists who study eruptions on the Earth, right? And most of those are at highly oxidized conditions. People working on like subduction zone, volcano hazards, and things like that. So we have really great constraints on water and carbon dioxide, and very poor constraints on just about everything else. I think the community has really recognized this gap and has really started pushing down to lower oxygen fugacities, where, you know, especially sub-Neptunes with a hydrogen-dominated atmosphere, the oxygen fugacity is going to be relatively low. In particular, constraining hydrogen H2 solubility. There's very little experimental data on that yet. And the other problem is pressure. The atmosphere magma ocean interface for a sub-Neptune is probably well below the depth at which most volcanoes on the Earth operate, right? So again, we have good constraints on solubilities for Earth-relevant volatiles at pressures up to about a GPa, maybe a little bit higher, whereas atmosphere magma ocean interfaces maybe 8 to 10 GPa. Right, so that's another area of where we're just lacking data. The other issue is mixed volatiles. We have a lot of these in isolation, but you can get very non-ideal solution effects once you start mixing things together. So that's true in a lot of areas, like metallic alloys. If you dissolve more than 3 volatile elements in a metallic alloy, we don't actually know how it behaves. Yeah.
If I can just comment on it, excellent point. I was going to say I was gratified to see the work by Kim, because there's just so little work on hydrogen. For some reason, people don't want to work on hydrogen experiments with high pressure and high temperature. I don't understand why. But also, just going off of the major elements. If you go off prototype, which is the standard mantle composition for the Earth, the experimental data runs pretty thin.
That's right.
So, Laura?
Lauren Weiss, University of Notre Dame. Wonderful talk. Thank you so much. So I'm, again, really curious on this H2 perfectly reducing idea. And this might be a question for you, but it might also be a question for the disk people in the audience, people who work on chemistry of disks, and especially detections of water in inner protoplanetary disks. Could this mechanism apply for the kind of solids that we might expect to exist in early disks? I guess really where I'm going with this question is, right, we have this question of, okay, if we get water in the inner solar system, how did we get it there? One way to get it there is to actually have sort of solid icy things from beyond the ice line in the disk physically move all the way in. Would an alternate possible mechanism be to take rocky stuff, which doesn't have to form quite as far out, transport it into, or even have it not migrate that much, but then have it undergo this kind of chemistry to produce the kind of water that we observe? Is that actually a viable pathway that's consistent with observations?
So I think part of that has to do with what the initial conditions in the disk are. I'm going to defer to all the disk people, but my understanding there's a lot of questions on inheritance of chemistry versus whether the chemistry is happening in the disk itself. But as somebody who's trained by a cosmochemist, an equilibrium chemistry cosmochemist, the way you model the solar nebula composition is that the oxygen abundance in the solar nebula is larger than the combined abundance of the rock-forming elements that want to take oxygen out of the atmosphere. And so the remaining oxygen gets partitioned between carbon monoxide and water vapor. So there is already some intrinsic water vapor and oxidized carbon species in a protoplanetary disk gas. I think my point here is to say that then adopting a pure H2 atmosphere for any planet is not realistic, right? Because there are other gases there. They are at the more trace level, maybe 10 to the minus 3 for water vapor in the protoplanetary disk, but they're there already. If you instead just have pure hydrogen that you dump on top of this, it's going to want to equilibrate. And it won't actually equilibrate at the protoplanetary disk abundance, right? Because now you're removing oxygen from other species that would happily keep it. So I'm not sure if that's necessarily happening in the disk itself, but there's certainly potential regions where you might be depleting an area in water vapor locally. You transport grains, and then maybe you have chemistry happening like that within the disk elsewhere also. So lots of heterogeneities in disks where you can get weird kinds of chemistry to happen too.
Thank you.
Okay, I think that's time. Let's give Laura another big thanks for this excellent keynote talk.